Good morning, everyone. Welcome to another lecture. In the last lecture, we briefly introduced the concept of set and its notations and also discussed the various types of sets. We defined a set as a well-defined collection of objects and discussed the types of sets like null set, finite and infinite sets, equal and equivalent sets, subsets, supersets, proper sets and power sets, and also we discussed the sets like disjoint sets and universal sets. Today, we will discuss Venn diagram and set operations, mainly the union of sets and its properties. See, the most of the relationship between the sets can be represented by the mean of diagram, which are popularly known as Venn diagram. Therefore, the Venn diagram is a graphical representation which is used to illustrate the relationship between the sets, which named after or invented by the John Venn. And this Venn diagram consists of rectangles and closed curves, usually circles. The circles actually represents the sets, and the entire space within the rectangle represents the universal sets, which are generally denoted in terms of U. If we have two sets, for example set A and set B, and these two sets have some common elements, then these are called an overlapping sets. The overlapping regions shows the existence of common elements between the sets. Now, we already said that Venn diagram consists of rectangles and circles. Each circle in the Venn diagram represents a set. So the elements of sets are placed inside or within the boundary of the circle. And we have two sets here, for example, say the set A and the set B. And the overlapping region between the circles, that is indicated the elements that are common in both sets. So the degree of overlap, that means the width of overlapping region, that means this particular area is entirely depending upon the extent of shared elements. The non-overlapping region within this each circle represents the elements that are unique to that particular set. And here the rectangle surrounded by the circle that may be represented as universal set, which include all the elements under consideration. So in this way, we can interpret the circles and rectangle in a Venn diagrams. For example, we have a universal set that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the set A is equal to 1, 2, 3, 4, 5. And set B is equal to 5, 7, 9. See, I would like to show these sets by using the Venn diagram. So I am representing these sets by using the Venn diagram. And the rectangle region that is representing, it is the universal set, that is U, which contain all the elements from 1 to 10. Here set A is represented by the circle on the left. So this is the circle A which is representing set A, which containing the elements of 1, 2, 3, 4 and 5. And set B which is represented by the circle on the right, which contain the element of 5, 7 and 9. The overlapping region here in the circle is representing the common to both set A and set B. So in this case, see here, the 5 is the overlap. That means 5 is present in both set A and set B. So here 5 is overlap because both set A and set B share the common element, that is 5. So two sets are said to be intersecting or overlapping if they have at least one common element. So in this set we have 5 is the common element and considered as the overlapping sets. And the remaining elements, that is not belongs to set A and set B, which will be come under the area of rectangle and outside the circle. Okay, so in this way we can represent the given universal set, set A, set B by using the Venn diagram. Now we have another example. Given the universal set of 1 to up to 10, and the set A is equal to 1, 2, 3 and set B which is equal to 7 and 9. In this case there is no overlap because set A and set B do not share any common element. Such sets are generally called a disjoint sets, or here the intersection is empty because there is no common element in the set A and set B. So it is also known as mutually exclusive sets. Disjoint sets are also known as mutually exclusive sets. That means no element that are in common. In other words, the intersection of disjoint sets is an empty set. That is, intersection in this particular case is empty set. If two sets are disjoint, it means that they do not share any common element. So in that particular case, we can represent the Venn diagram here. See the circle A, which is representing for this set A, which is having the element of 1, 2 and 3. And here the circle B, that is having the elements of 7 and 9. And see here, there is no common element. That's why there is no overlapping region here. These two sets are the disjoint set, or these are the mutually exclusive sets. And the remaining elements of the union that can be represented within the rectangle and outside the circle. Now we have set operations. See, set operations are the mathematical operations that can be performed on the sets to create a new set which is used to analyze the relationship between the sets. Sets are the collection of distinct elements, and the set operation help us to perform various tasks related to the combining, comparing or extracting the elements from the sets. So here we are going to discuss some fundamental set operations. So the first one is union of sets. See, the union of two sets is the set of elements that is belongs to either set A or set B or in both, which are generally denoted by A union B. See, here it is generally denoted in terms of A union B. See, it consists of all elements that are in set A or in set B, including any element that are common in both sets. So here this symbol is used to denote the union operation between these sets. Mathematically, the union of set A and B is defined as, see, A union B, which is equal to the set of all elements of X, that is such that X is belongs to A or X is belongs to B. So when you can read this particular thing, that is the union of set A and B is the set of all elements of X such that X belongs to set A or X belongs to set B. So thus A union B consists of all elements that are in set A or set B. See, we can represent the union of sets by using the Venn diagram. So the union correspond to the entire region covered by the both circles representing set A and set B. Here this is the set A and this is the set B, and we have overlapping region as well. So here the entire region covered by both circles representing set A and set B. So the union consists of all elements from both sets, including the overlapping region, represent the common elements shared by both sets. Therefore, see here A union B is the shaded portion, or it is the shaded area in the given Venn diagram. So this entire area will be considered as the A union B as per the Venn diagram. Now we are going to consider one example. If we have two sets, that is set A which is equal to 1, 2, 3 and set B is equal to 3, 4, 5. Then the union, that is A union B, would be 1, 2, 3, 4, 5, as it includes all unique elements from both sets without writing the repeated elements. So this is the A union B, especially by considering the set A and set B. Now we have another example. Given set A is equal to 2, 4, 6, 8 and set B is equal to 6, 8, 10 and 12. So here the union of sets, that is A union B, is the set of all unique elements from the both sets, combining the elements from set A and set B and ensuring that common elements are included only once. Therefore, here the elements 2, 4, 6 and 8 from the set A and the elements 6, 8, 10 and 12 from the set B. And the common elements here, the 6 and 8, we are included only once, especially while we are calculating the union of sets. So we can write A union B here, it is 2, 4, 6, 8, 10, 12. 6 and 8 will be written only once. Now, we will discuss various properties of the union operations of sets, which are essential for understanding how set interact and how the union operation behaves. See, the first one is commutative law. That is A union B which is equal to B union A, which represents the commutative law for the union of sets. This law is actually states that the order in which you take the union of two sets does not matter. Whether you take the union of set A with set B or the union of set B with set A, you will end up with the same set. So the commutative law for the union emphasizes that the union operation is commutative and resulting sets is the same regardless of the order in which you combine the sets. For example, see, set A is equal to A, B, C and D. And the set B is equal to D, E and F. So the union of set A and B is the set of all unique elements from both sets. So in this case, A union B is equal to A, B, C, D, E and F. So now we are going to prove the commutative law for the union of set states that A union B is equal to B union A. So here we are going to consider B union A. So if you go for considering the B union A, which is the set of all unique elements from both sets, that is also equal to A, B, C, D and E, F. Hence we can say that the commutative law is called A union B is equal to B union A. So here the order in which you take the union of two sets does not matter. Now the another property, that is the union of sets is associative. That is A union B union C which is equal to A union B union C. So it actually represents the associative property for union of sets. And this property is actually states that the grouping of the sets when performing the union operation does not affect the results. Mathematically, we can say that the associative law expressed A union B union C which is equal to A union B union C. So this means that if we have three sets, that is set A, set B and C, then the union of these sets, whether you perform the union of A and B first and then union result with C, or if you take the union B and C first and then union result with A, you will get the same sets. So here, for example, the set A is equal to 1, 2, 3 and set B is equal to 3, 4, 5 and set C is equal to 5 and 6. Then A union B union C, that we are going to take, that is left hand side of the formula, that is A union B union C. So first here we are calculating A union B. So here A union B, that is 1, 2, 3, 4, 5. So A union B will be the A 1, 2, 3, 4, 5. Then we are going to take A union B union C. So it is 1, 2, 3, 4, 5, that is A union B. Then union, what is C? It is 5 and 6. So if you combine it, then the A union B union C, which is equal to 1, 2, 3, 4, 5. 5 is repeated here, so we are considering only once. Then we have 6 here. So it is 1, 2, 3, 4, 5 and 6. Now we are going to consider the right hand side formula, that is A union B union C. So here first we are going to calculate, that is B union C. So B is 3, 4, 5, C is 5 and 6. So B union C, that is 3, 4, 5 and 6. This is B union C. Then we are going to integrate with A union B union C. Then it will become C. A is the 1, 2, 3. Union B union C, that is 3, 4, 5, 6. So if you take the A union B union C, then it will become 1, 2, 3, 4, 5, 6. So here you just see the A union B union C, that is equal to 1, 2, 3, 4, 5, 6, and A union B union C, which is also equal to 1, 2, 3, 4, 5, 6. So hence we can say that the A union B union C, which is also equal to A union B union C, we have successfully demonstrated the associative property of union of sets. Thus, this property shows that the grouping of sets when performing union operation does not affect the results as long as the order of the sets remain the same. So the union of sets is associative. So the another property, which is law of identity elements. So here it is A union phi, which is equal to A, which represents the law of identity elements for the union of sets. So the empty set, that is phi, is the identity element for the union operation. So we can say that A union phi, which is equal to A, which actually states that the union of any set A with empty set results in the original set A. So the reason for this is, see, the empty set has no elements. So taking the union of any set with the empty set does not introduce any new elements, leaving the original set unchanged. So we can say that A union phi is equal to A. We can prove it by using an example. See, consider set A is equal to 1, 2, 3, and we have another set, that is phi, null set. Then when you perform the union of set A with empty set, that is A union phi, which is equal to A, that is 1, 2, 3, union phi, that is empty set, so it is also equal to 1, 2, 3. Hence we can say that A union phi, which is equal to the original set. Now the another property, that is idempotent law, that is A union A, which is equal to A. It actually represents the idempotent law for the union of sets. And this law actually states that the union of sets with itself results in the original set. Mathematically, we can say that the idempotent law for the union of set is expressed as A union A, which is equal to A. So here see, the elements in this set are unique, and including the same elements in multiple times in a particular union does not change the sets. For example, see, set A is equal to 1, 2 and 3. And if you are going to calculate, that is A union A, then it will be, see, 1, 2, 3 union 1, 2, 3. So here it is also equal to 1, 2, 3, that is equal to A. So it can also say that if you go for conducting repeated union with the same sets, then also has it no additional effect will be happened. So here we can say that A union A union A union A, which is also equal to A, because applying it multiple times, so the same set does not produce any different outcome beyond the first application. Therefore, A union A union A union A is equal to A. So this is the idempotent law. Now we have another law, that is law of universal, that is identity law. That is A union universal set which is equal to universal set. A union U which is equal to universal set, which represents the fact that the union of any set A with the universal set is equal to the universal set. Mathematically, we can say that if A is the subset of universal set, then the union of A and U, or the union of A and universal set which is equal to the universal set. This is because the union of any set with the universal set includes all the elements from both sets. But since A is the subset of the universal set, no new elements are added to the universal set. We can prove it by using an example. See, we have a given universal set that is equal to 1, 2, 3, 4, 5, 6, 7. And the set A is equal to 1, 2 and 3. Then the identity law for the union states that the union of any sets with universal set is equal to the universal set itself. So here, see, A union universal set which is equal to A here 1, 2, 3, union 1, 2, 3, 4, 5, 6, 7 which is equal to 1, 2, 3, 4, 5, 6, 7 which is also equal to the universal set. So this result actually shows that the union of any set with universal set result in the universal sets, because the universal set already contain the all elements. Now we have a particular example, that is set A is equal to 1 and 2, set B is equal to 2, 3 and set C is equal to 3 and 4. We want to calculate A union B union C and A union B union C, and we want to verify the associative law. So the union of set is said to be associative when A union B union C which is equal to A union B union C. So it shows that the grouping of sets when performing the union operation does not affect the result. We are going to prove by using this particular example. See, first here we are going to consider A union B union C. So here B union C which is equal to, what is B? It is 2 and 3 union, then C which is equal to 3 and 4. So B union C which is equal to 2, 3 and 4. 3 is repeated here, so we are writing only once. So it will become 2, 3 and 4. So this is B union C. Now it is A union B union C. What is A? Which is 1 and 2. So it is 1, 2 union. Then B union C which we are already estimated here, it is 2, 3 and 4. So A union B union C which is equal to 1, 2, 3, 4. 2 is repeated here, but we are going to consider only once. So A union B union C which is equal to 1, 2, 3 and 4. Similarly, we are going to consider here the A union B union C. So here first we are going to calculate A union B. See, what is A union B? A is 1, 2, B it is 2, 3. So A union B here it is 1, 2 is repeated, so we are going to consider only 1, 2, then 3. So it is A union B is equal to 1, 2, 3. Then A union B union C. A union B which we are already estimated here, it is 1, 2, 3 union C which is equal to 3 and 4. So 1, 2, 3 union 3, 4 which is equal to 1, 2, 3. 3 is repeated, so we are going to consider only once. Then we have 4 also. So A union B union C which is equal to 1, 2, 3, 4. Here also A union B union C which is also equal to 1, 2, 3, 4. So we can say that the union of set is associative. It actually shows that the grouping of sets when performing the union operation does not affect the results. We have one more example. See, take x is equal to 2, 4, 6 and another set y is equal to 1, 3, 5. We want to compute x union y and y union x and shows that the order of the union does not matter. That means here the question is actually related to the commutative law for the union of sets. It says that the order in which you take the union of two sets does not matter. So when you take the union of set A with set B or the union of set B with set A. So here it is x union y or y union x, you will end up with the same result as per the theory. Now we are going to prove the same by using this particular example. So we have this set x is equal to 2, 4, 6 and set y is equal to 1, 3 and 5. So first we are going to consider x union y which is equal to 2, 4, 6 and here 1, 3, 5. So we can write it is the 2, 4, 6 union 1, 3, 5 which is equal to 1, 2, 3, 4, 5 and 6. So x union y which is equal to 1, 2, 3, 4, 5, 6. Similarly, now we are going to consider y union x. What is y? Which is equal to 1, 3, 5. Union, what is x? It is 2, 4 and 6. So if you go for calculating y union x, then it will become 1, 2, 3, 4, 5 and 6. See here, x union y and y union x, which are both are equal, that is 1, 2, 3, 4, 5 and 6. So here we are proved that the commutative law, that is x union y is equal to y union x, that shows that the order of union does not matter. So we are going to conclude here. In this lecture, we discussed what actually Venn diagram means and shown that it is a graphical representation used to explain the relationship between the sets. Besides the Venn diagram, we also discussed today one of the popular set operation, that is the union of sets and its various properties. I hope you understood all these operations very well. In the next lecture, we will discuss the intersection of sets and the difference sets and also its various properties. So we'll see in the next lecture. Thank you.